So in the previous lecture, we started with the concept of pulse code modulation and quantization. We've seen that the quantization is a very important building block for PCM. Okay, we have had a basic brief idea about the quantization in the previous lecture. We'll continue forward. So in case of quantization, what we do is the dynamic range in which the samples are distributed. Let's say it's from my 0 to V. This dynamic range is divided into L number of equal steps. So this range is divided into L number of equal steps. And the middle point of each step is assumed to be the quantization level. So middle point of each step is nothing but your quantization level. So L would be the number of steps, or you can say the number of quantization level. So any sample value which is coming in this range will be quantized to this point. Any sample value coming in this range will be quantized to this. Similarly, any sample value coming in this range will be again quantized to this level, and so on. So this is the overall process of quantization. That means we are limiting the number of samples from infinite to a finite value that is equal to the number of quantization level. Okay. So the reason why we go for quantization after sampling is so that we can perform the encoding process thereafter easily, because we are limiting the number of samples here. Now since the samples will be limited, so the number of bits required to encode it will also be less, right? So clearly we can see that the maximum value of quantization error can be delta by 2, right? And if n is the number of bits per sample and L is the number of quantization level, so we can easily correlate L and n as L is equal to 2 raised to power n. So if there are 4 different quantization levels, as seen in this case 1, 2, 3, 4, we can use n is equal to 2 number of bits to represent each quantization level, and we know the combination for n is equal to 2 possible combination is 0, 0, 0, 1, 1, 0, 1, 1, right? So with the help of these combinations we can represent quantization level. And the step size delta can be equal to V max minus V min divided by L, where V max minus V min gives you the dynamic range of the samples, or the range in which the samples are distributed. So if we just take an example of a sinusoidal signal with amplitude AM, this is AM, this is minus of AM. So the dynamic range here is twice of AM. So the step size would be twice of AM divided by L, or you can say twice of AM divided by 2 raised to power n. Okay, and the quantization error is nothing but the sampled value minus the quantized value. This will give you the quantization error. And maximum value of this quantization error will be equal to delta by 2, that we've already seen, plus minus delta by 2. Now coming to the bit duration, if we suppose that the sampling duration is TS is the sampling duration, that means we sample the signal at every TS instant, 0, TS, twice of TS, so on, right? So the bit duration, if you have a look at it, we consider an example where n is equal to 2. So there are 2 bits per sample, right? So let's say this bit represent 0, 1. This sample represents 0, 1. Then it represents 1, 0. Right? Each sample represent 2 bits. Okay. So that is what we have done here. Each sample represent 2 bits. So the bit duration would be this TB, right? And TB will be equal to TS by 2. Alright. So in general, this is for the case when n is equal to 2. So in general, we can say that for n number of bits, TB, that is the bit duration, is equal to TS by n. This is one important relationship. And moving on, if we want to find out the bit rate, this is the bit duration. Now if we want to find out the bit rate, we know the unit of bit rate would be bits per second. So this could be equal to bits per sample into sample per second. So this combination can give you this unit, that is bits per second. So bits per sample is nothing but your n, and sample per second is nothing but your sampling frequency, f of s. So this gives you the relationship between the bit rate and the number of bits per sample and the sampling frequency, or we can say RB is equal to n by Ts. So this is your bit rate. Now if we talk about the transmission bandwidth of the channel, maximum transmitter bandwidth. We talk about maximum transmitter bandwidth, and let's take a few examples. That first example is 1 bit is transmitted at a time. 1 bit is transmitted at a time. So bandwidth would be equal to 1 upon TB. If we look at the spectrum of it, when we are transmitting only 1 bit, it spreads from minus 1 by TB to 1 by TB. Okay, so the bandwidth would be equal to 1 upon TB. Similarly, if 2 bits are transmitted, bandwidth would be equal to 1 by 2 TB, or it is equal to RB by 2. Alright. Similarly, if 3 bits are transmitted, it becomes 1 by 3 TB. Alright, and so on. So if a channel has, let's say, bandwidth equal to RB by 2, then we can say that it will allow the signals having bandwidth RB by 3, RB by 4, RB by n, so on. Okay, so we can say the minimum bandwidth required is RB by 2, and this is the standard bandwidth, because in practical cases the minimum 2 bits are at least transmitted in a bunch. In practical scenario, at least 2 bits are transmitted in a bunch. So this is the maximum bandwidth of the channel, RB by 2, and if the channel has this bandwidth, it can easily transmit the signals having RB by 3, RB by 4, or RB by n bandwidth, signals having these bandwidths. Okay, so the maximum transmission bandwidth would be RB by 2, because in practical scenario we assume that at least 2 bits would be transmitted in a bunch. Otherwise there is no point of multiplexes here. Okay, let us do some examples based on this concept. We are given with a message signal. A message signal is given, that is mt equal to 10 cos 8 pi into 10 to the power 3 t is transmitted through 4-bit PCM. Okay. Find all the parameters. This is the question. We are given with the message signal and that has to be transmitted using a 4-bit PCM. That means we are given with the value of n that is equal to 4 bits per second. Okay. And we are also given with the message signal that is 10 cos 8 pi into 10 to the power 3 t. So we can find out important parameters from here, that is AM would be equal to 10, f of m would be equal to 4 kilohertz, right? Value of n is equal to 4, so the number of quantization level L would be equal to 10 raised to the power n, that is 16 quantization levels. Moving on, what would be the step size of the quantization levels? Step size delta. We know step size is the dynamic range V max minus V min divided by L. So what is V max by V min in this case? It's a sinusoidal signal. AM is equal to 10. So obviously this is a sinusoidal signal. This is AM. So the dynamic range is twice of AM. Right? So 2 into 10 divided by L is 16. So this will be your step size. Now next is your sampling frequency. What will be the sampling frequency? So sampling rate is not mentioned over here, right? So the standard way to find out sampling frequency is to determine the Nyquist rate, that is twice of Fm, because we know as per the sampling theorem the sampling frequency should be greater than equal to twice of Fm. So we assume it to be twice of Fm, that is the standard Nyquist rate. So sampling frequency will be 2 into 4k, that is 8 kilohertz. Alright, what will be the maximum value of quantization error? We know it is plus minus delta by 2. We already know the value of step size, so it becomes plus minus 20 by 32 volts. Next, what will be the bit rate? RB. Bit rate, we know it is n into f of s, so it is 4 into 8, that is 32k. This is the bit rate. And then what will the bit duration? TV is equal to 1 upon RB, so you can easily find out this also. Then what will be the maximum bandwidth? Bandwidth is equal to RB by 2, and that will be equal to, what is RB here? RB is 32, so bandwidth comes out to 16k. Moving on to the next type of a question. A message signal of amplitude AM is equal to 20 volts and frequency equal to 5 kilohertz is transmitted through 256 level PCM system, and we are given that the sampling rate is 25% higher than Nyquist rate. Find all the parameters. This is the question given to us. A message signal of amplitude 20 volts and frequency 5 kilohertz is given and is transmitted through a 256 level PCM. 256 level PCM means we are given with the number of quantization levels, and the sampling rate is given that is 25% higher than the Nyquist rate. We are supposed to find out all the possible parameters. We are given with AM, that is 20 volts, FM is 5 kilohertz, value of L is 256, and the sampling frequency Fs is your Nyquist rate plus 25% of Nyquist rate. 25% of Nyquist rate. You know L is equal to 2 raised to power n equal to 256, so value of n comes out to be 8. That is 8 number of bits per sample are available, right? And Nyquist rate is equal to, we know, twice of f of m, that is equal to 10 kilohertz. So the sampling frequency Fs, it is 25% higher than the Nyquist rate, so it would become 10k plus 25 by 100, comes out to be 12.5. So, sorry, this is Fs is 1.25 of 10, that is 25% higher of the Nyquist rate, which is 12.5 kilohertz. Now finding out the step size. Step size is the dynamic range V max minus V min divided by L. It comes out to be twice of the, we know it's a sinusoidal signal and AM is given as 20, so it becomes 2 into 20 dynamic range divided by L, that is 256. So it comes out to be 0.15625 volts. Next is the maximum value of quantization error, that is plus minus delta by 2, that can be easily found out. Next is bit rate, that is n into Fs, where we know n, we know Fs, so that can also be found out. TB is 1 upon RB, this is bit duration, then bandwidth is equal to RB by 2, so you can find out all the other parameters accordingly. You may note down one more different type of a question here. It says that a sinusoidal message signal is transmitted through PCM where the maximum value of quantization error can be at most 2% of peak to peak amplitude of message signal. Question is to find the number of bits per sample required. Let's try this question on your own. Moving on, we can have a look at the characteristics of the quantizer. So on the x-axis, let us divide the axis in terms of the levels. Let's say starting from origin is 1.